now that we've gotten this far, everyone knows everything they need to know about Python. You're ready to program. How do you actually go about, organizing your data and your analysis and putting it all together? So the title you might have seen is reproducible workflows. So what do I mean by that? So what is a reproducible workflow? So technically, one description might be that you have complete provenance from going from raw data to final results in figures. What that means in practice is you should be able to recreate everything that's created by your code with a single command just by typing run my analysis. And so that way, that's what I mean by complete provenance, is that you can then go back and look at your code and see from the raw data that came off of your instrument or your, in my case, your telescope or whatever you started with from your analysis, how everything was created to the final results that go in your paper. So why do you want to bother doing this? Because it can be harder than not doing it in some cases. So one reason is it's just good science to do this, so that if anyone asks, you can go back and look at how things were actually done. It can save you a lot of repetition in the end if you do set up your analysis so that you can just type one command. I don't know, at least how I do analyses, I end up modifying them a lot, and you end up rerunning the same thing. And so the more you can automate, the better off you are. Who can remember what they were doing 6 months ago? So if I'll stop working on a project and switch to something else and come back and be like, where was I? What sequence of commands did I need to write to run to produce this output? If you have a script that does it for you, then it's obvious you just look at the script. And finally, we haven't talked a lot about, or hardly at all about version control, but if you combine this with version control, you can then recreate your entire analysis at any stage going back in history. So I'm going to sort of do an example of doing a real world-ish project. So I'm going to start by creating a clear directory structure for the project. We're going to add some data, and I'll show you how to download some test data. Write some core science code. So in this case, write, I mean copy in a few modules that I have as examples. We're going to write a test. And finally, create a run all.py script to run everything together. OK, so as an aside, what I work on is cosmology. And so the example I'm going to deal with takes an example from my research. So this has to do with the discovery that the universe is accelerating has been accelerating since the Big Bang, or is accelerating at the present time, which people discovered in the late 90s and actually had the Nobel Prize awarded for it in 2011, partially to people at Berkeley. So this kind of cartoon chart kind of shows you the size of the universe in terms of the distance between galaxies as you go forward in time going up. So how this was discovered was using supernova, which is what I work on, which look like this, artist's rendition. And roughly how you can use these to determine how the universe is expanding is that you look at the brightness of supernova looking back in time, looking further away, and how bright the supernova appears to you tells you something about how long ago it happened, right? And the redshift of the light, which I won't go into too much, tells you about the scale factor of the universe. So really just putting those two things together, observations of various supernovae, each one knowing the brightness and the redshift, can tell you how the universe expanded. OK, so I think that was all I had in the lecture there. So I kind of want people to follow along if you can, just to see how things work. So I'm going to start with a empty directory that I'm calling Supernova. So to follow along, just go to anywhere on your system and create an empty directory. And so the first thing we're going to do is create a directory structure that we think is going to be useful for our project. So it obviously depends on what kind of data you have and what kind of results you're going to have, what you do. But in this case, I'm going to just make a directory called data to have my raw data in. I'm going to make a directory called results, where I'm going to put like text files that come out of the analysis. And I'm going to make a directory called plots to hold figures that are created by my scripts. OK. I think that's all we're going to need. And then, so the next thing we're going to do is actually get this piece of test data that we're going to work on. And so you see I have a download data script. And so if you go to the schedule and scroll down to the scientific workflows with Python, let me make this a little bigger. I've got a bunch of links over here on the side. And you can directly right-click on these and do save as, and just save them into that directory you just created. So I've already gotten download data.py. OK, so you should be able to run this download data. It's just a script. You don't have to look at it. It's really just to get the data. Hopefully that will work. And if everyone does it at the same time, it'll swamp the network. No, it's not that bad. All right, so now if you've done that in data, you should see a file called sndata.fits. OK. And all right, so moving on. So the first thing you might do if you have some raw data, you don't necessarily know what analysis you're going to do right away. You might kind of need to explore the data a little bit. So to be realistic, we've got an IPython notebook that we're going to start with. So you can do the same thing. You can directly right-click on this. You don't have to go to the GitHub page and click raw like we've been doing with the other ones. I just put the raw link in here. So you should be able to right-click save as that. I've got it locally in another directory. So I'm just going to copy it over. OK. So, bigger. All right, so let's see what this data file we have, which is this sndata.fits file. Let's see what it has in it. So fits, by the way, is this arcane format that's been used since the 70s in astronomy. And if you've downloaded the whole Anaconda distribution, you should have this AstroPy package that I'm using, which has a bunch of core routines used in astronomy. If you did something else, if you just have mini Conda, you can do Conda install AstroPy, should work. If you're not using Conda, then I'm sorry. OK, so let's open that up. So here I've loaded the data into a variable into a record array or a structured NumPy array. So you can see that SNE is a variable. It's a NumPy array. It has 277 entries, and it's basically a tabular structure. So it has these column names. So the first thing we're going to do is just, all right, so this is kind of what the data looks like. In practice, we only care about a few of these columns, so I'm just going to get references to these as normal arrays, this being the redshift of each supernova, Z. The MB is the brightness, the error on the brightness, and then two other things about each supernova, the color and this color C, and this X1 parameter, which don't worry about too much, but we're going to use those later. So let's just plot these. We're going to plot the brightness as a function of redshift and see what it looks like. So this is a helper function to make the plot. And all right, so we make the plot. So if I can make this a little smaller so you can see it all. All right, so what you're seeing here is each one of those points, there's 277 points. Each one is a supernova. The y-axis is brightness in astronomer units. So actually, dimmer is higher up. Dimmer is larger numbers. That's how we do things. Don't ask why. And the x-axis is redshift. So as you get to dimmer and larger redshift, you're looking further back in time. And actually, the shape of the curve that these map out tells you something about the contents of the universe in terms of how much dark matter and dark energy there is, because the ratio of dark energy to dark matter in the universe determines how the universe expands. So that's really the name of the game in the research I do, is measuring that curve really accurately. So it turns out that there's some corrections we can add to reduce the scatter in this plot. So we're going to take our MB parameter, the brightness, and use the C and X1 variables for each supernova and create a corrected brightness. And then when you plot that, you see that the scatter reduces pretty significantly. And I said that the contents of the universe in terms of dark matter and dark energy affects the shape of the curve. We can overplot a theoretical prediction of what the curve should look like for a given content of dark matter. So I'm going to do that now. So this is for a contents of dark matter being 0.25 in some units. And if I overplot that, you see that, OK, so that kind of fits the data, but not really. It's kind of under here. So maybe I'll try a different value, 0.5, and overplot that. OK, that didn't help. But what you should get from this is that we can hope now to be able to fit this value to the data. So that's what we're going to do in this analysis. We have this data. We're going to sort of write a whole set of programs and organize them to actually do this fit and output some results. OK, so maybe I should say as an aside, all right, so I've been doing this in the notebook so far. You could imagine just continuing on and doing your entire analysis in a notebook. At some point, that gets out of hand. I'm sure some of you have, written, thousands and thousands of lines of code to do your analyses in the past, and doing that all in a notebook would just get very confusing. You need some organization. So at some point, you need to shift out of the notebook and start putting things in modules and reusing code and doing organization that way. So this is kind of, for me, this is the point where I do that. After doing some exploratory analysis, I'll say, OK, now I kind of see what I need to do. Maybe I need a fitting function, and that's going to go in a module. And I need some plotting functions, and those are going to go in a module, right? OK, so you can go back to the schedule and download these other Python files, data utils, fitting.py, and run all. You don't need to get the test one yet. So I'm going to go ahead and close down the notebook, because I'm done with that for now. OK, so your directory should look something like this. You've got your notebook that we were just looking at, but you've also got some Python modules, fitting.py, data utils, and run all. So I've sort of, at this point, I've sort of made some choices about how to organize things. And just to show you what I've done here, let's look at data utils. OK, so this module that I have just has a single function in it. But you can imagine needing, in your analysis, needing to read lots of different types of data. So you might want to organize that into a separate module, right? So that's what I've done here. So I have a function called read sn data that reads this particular file format. And it does the things I was doing in the notebook, doing these conversions, and just returns to me a dictionary with the values I care about, right? So then in this run all script that's going to do all of our analysis, this is the first thing I'm doing here is using that data utils .read sn data file. And you can see sort of the important thing here is that those other two files, data utils and fitting, are Python modules that I can import with import statements like you would use for any standard library thing, as long as this script is in the same directory as those modules.
Is this Sublime? Is that what that is?
The editor?
Yeah.
This is just Emacs running in a terminal. It's sort of the simplest thing. Huh?
So it's like Nano?
Yeah, in the same way that Nano runs in a terminal. Yeah. If you have Emacs and you run with the -NW flag, it will run in a terminal instead of popping up a new window. OK, so then what have I put in this fitting module? So this is stuff I didn't have in the notebook. So to actually do the fitting, I guess I don't really have time to go into it completely, but this is an example of using SciPy. So to actually do this minimization and fit my function to the data, I'm using the SciPy optimize module. So if you need to do a function minimization, then there's a lot of different types of routines. The one I'm using is sort of like, I think, the most basic. I forget what the actual algorithm it uses is. But that's sort of like the first go-to place to look for doing optimization. So the main point of this is I've got a function I'm going to use in my main script called fit cosmology. It takes the 3 arrays representing the redshift, the brightness, and the error on the brightness for each supernova. And you can see I have this nice doc string here saying, reminding me what the parameters are with the type, the description, and then the return value down here. So I would recommend when you are writing your code to pick some, this is a particular format of docstring. You can make other choices, but just be consistent and try to remember to actually do it.
So it's very faint, the red and the blue from here. Can you keep it white? Use the eye. You just cat the thing and show it, cat it. Not done.
All right.
Since you're not going to edit it, you can just cat it.
Yeah. people see that? Sorry, you don't get the syntax highlighting this way, though. Right, so yeah, so what this function is doing is it's really just a two-line function that calls the minimizer fmin on a chi-squared function. You feed it some initial parameters for these two parameters we're going to try to optimize. And you, for the interface to this is you can feed it additional arguments that get passed to the chi-squared function. And then at the end, we're going to create a cosmology with those parameters and return that. So this should be the optimized cosmology. OK, so let's take a look at our last thing I have here, which is the script that's going to run all of our, it's going to put everything together and use these two modules. How much dark text is there here? I think this looks OK. The blue, it looks amazing on my laptop. This color scheme is awesome. The blue here is just print statements, and this guy is a with statement. So don't worry too much about it. All right, so this is sort of like, the point here is that this main script that runs the analysis shows you the main flow of the analysis. Obviously, this is a very simple analysis, but all we're doing here is we have a step that first we read the data, then we're going to do this correction to our data that I illustrated in the notebook. And then in this line, we're actually doing the fit. We're calling the fit cosmology function from the fitting module that we have. And then we're going to plot the data, which is pretty much just using the same sort of plot that was in the notebook, but I've put that into a module also. And we're going to save that to the plots directory. And then finally, we're going to write the results file into the results directory. So if you actually run that, you should then see that in plots, we have our plot that we created. And if we look at that, hopefully it will, no, right, it's in plots. OK, it looks like a good fit now. Yay. So what are the parameters of the universe that best fit the data? They are written to our results file. So this omega matter parameter is 0.41, which is significant because it means that if it were 1, we would have no dark energy. The fact that it's not 1 means that 60% of the universe is dark energy. The real number is actually more like 70, so we didn't get exactly the right answer, but that's because supernova cosmology is harder than this. Not a lot harder, but it has a little bit more subtleties. OK. Let's see. So something I haven't done, though, is write any tests, right? Since I have some time, we're going to go ahead and do that. So one thing I might want to test in this code is to make sure my fitting function actually does what it should. So there's different ways you can imagine testing this, but one of the simplest is to create some fake data that you know the answer to, and fit the data and see if you get the answer you expect. So I don't have to write it all out. You can go ahead and download the test.py file from the web page. And OK, so hopefully you can see the blue OK. This is just an import statement. So I'm importing the fitting module that I have. And I'm writing a function that starts with test. I'm going to go ahead and create a cosmology where I know the answer, where the answer is 0.25. And then I'm going to create some fake data for my supernova, being redshift and brightnesses, where the brightnesses are generated from the cosmology. And I'm going to fit to the fake data. And then at the very end, I'm going to check that the value is what I expect. So actually, when I was doing this, I didn't know how good an answer I would get. So the first thing I tried to do was assert that my input cosmology had an H0 value equal to fitted cosmo.h0.value. So I tried to do this, and I use PyTest, so you can run the tests with PyTest and then the file name. Thanks. Test your tests. Right, so maybe you can't read the red here, but it's basically telling me that I asserted that 70, which is the input value, is equal to 70.000002, and it's not equal, right? So this is a case where this comes up a lot when you're testing real code, especially testing fitting code. You have to make some decisions about how close you need the answer to really be. Because if you're running an optimizer, it's going to stop at some point. It's not exactly the optimum, right? So what I ended up having to do was, here's a case where you can use the functions from NumPy that NumPy provides. So I'm using from NumPy testing import assert all close. So with this, you can say, OK, assert that this value is not exactly equal to this value, but that it's equal within relative tolerance of 10 to the minus 4. So with that, you can then do PyTest, and hopefully it will work. OK, yay. So most of the time, just as an aside, like personally, I won't write tests for all the code I'm writing, partially because it's not like mission critical that it all be right. And most of the time, I don't do test-driven development because a lot of times you're not really sure what the code you're writing really needs to do until you write it, because there may be some subtleties in the data, right? But I will write tests for some things where they're particularly tricky that I'm not sure if I've gotten right. For example, like sometimes you need to write out explicit gradients of your function you're trying to optimize. And personally, like I'm always worried that I've got the gradient calculated wrong. So I'll write tests for stuff like that. Or if I'm doing like fiddly things where I'm like, matching the size of rectangles, and I'm worried about swapping the axes, I'll write a test to make sure that I've got the axes ordered right, stuff like that. Yeah. OK. Josh, how much time do I have? A couple minutes. OK. In that case, let's see. I'll say a couple things. So one thing is, what I've done here is just put my data in the same directory as the rest of my project. In reality, like the project I normally work on, our data is too big to like live alongside the code. It's like several terabytes. So in reality, you might have usually want to split up your code from your data if your data is really that big, and have the data live in some other disk, and the code just points to it with file paths, right? If your data is small enough, then you can include it alongside the code, and maybe even include it in the repository if you have a Git repository. Yeah.
Is that like, do you still have it like local, or is it just is the data distributed?
Yeah. So I guess for me.
Implications for the speed of the.
Yeah, it really depends on what you're doing, but for the project we work on, we have our data at NERSC at the computing center, and so it's on like a shared file system. So it still looks local, but yeah.
Do you compile your Python to make it faster, or do you?
No, Python's not a compiled language, so.
Normally it isn't, but I thought you can compile it.
You can use an alternative interpreter. So the answer is a little tricky, right? There is a compilation step where the code as you've written it is a very simple compilation step that's cached. So actually, if you do ls minus a in this directory, if you run this, you'll see a __ pycache __ file directory. And that's where Python stores the cached modules it loads. But that doesn't actually make it run faster, it just makes it load faster. So the normal Python CPython interpreter, which is what we've been using in this whole thing, and which is what almost all of you are probably using, doesn't compile the Python in any meaningful way to make it run faster. There are alternative implementations of Python, like Jython is one of them, I think, or IronPython. I'm blanking. What's the one with the JIT? PyPy, right. PyPy. That can run some Python faster, but in scientific computing, most people use CPython for reasons I can talk about later. Oh, yeah. So one thing that hasn't been mentioned is, it's getting a little bit on a tangent, but that's OK. A project called Numba, where, so what Numba lets you do is it actually does allow you to write Python code that then gets compiled in what's called just-in-time compilation. So it gets compiled the first time you run it, and then each subsequent time it uses the compiled version. So you can write a subset of Python that it can handle that will run close to as fast as C or Fortran in some cases. So you might want to look into that.